And we're back for part 2, our very last video of the year. Okay, with that beautiful musical interlude, let's talk musical instruments. So we're going to talk a little bit about string instruments and wind instruments and how they actually make noise using standing waves and superposition. So we're going to look at fundamental frequencies of these different musical instruments and the harmonics that they can play. So let's start with string instruments. So string instruments vibrate at their fundamental frequency. So if I pluck a string, it will vibrate back and forth. That's one hump or one up and down. So if I pull a string and vibrate it, it'll go like that or like that, or straight through the middle, and that's one bump, and that's mode 1, which is the fundamental frequency, right? The first harmonic. So I can have an equation for that, and the equation for the fundamental frequency is that the fundamental frequency is equal to 1 over 2 times the length times the square root of the tension over the linear density of the string. So let's do a little practice problem, setting the tension in a guitar string. We could also call this tuning the guitar string. The 5th string on a guitar plays the musical note A at a frequency of 110 hertz. On a typical guitar, this string is stretched between 2 fixed points 0.64 meters apart, 64 centimeters. And this length of string has a mass of 2.86 grams. What is the tension in the string? Okay, so I know I can use the equation F1 equals 1 over 2L times the square root of the tension in the string over the linear density. I'm solving for the tension in the string, so I'm going to solve for that guy. I have the length, that's 0.64 meters. I have the fundamental frequency, 110 hertz. Now I got to figure out this linear density thing. And I remember that the linear density is equal to the mass divided by the length of the string. So the mass should be in kilograms. So 2.86 grams becomes 0.00286 kilograms divided by the length, which is 0.64 meters. 0.00286 divided by 0.64 gives me 0.00447. Okay? So the linear density is 0.00447 kilograms per meter, okay? Or 4.47 grams per meter. All right. Now I need to solve for that tension. So I'll plug in all my values and have 110 hertz equals 1 over 2 times the length, 0.64 meters, times the square root of the tension of the string, and that's going to be in newtons, so it's good that I converted to kilograms and meters because those are part of newtons, over the linear density, 0.00447 kilograms per meter. Okay. So step 1 is I got to multiply both sides by 2 times 0.64. So that would be 2 times 0.64 times 110, giving me 140.8 equals the square root of t over 0.00447. Square both sides. And then multiply by 0.00447, giving me 88.6 newtons. So T sub S equals 88.6 newtons of tension on that guitar string. And that seems like a reasonable value. That's what, 40 pounds No, 20 pounds. Sorry, about 20 pounds of tension. So that seems about right. Okay. Let's do a little stop and think. A standing wave on a string is shown. Which of the modes shown below on the same string has twice the frequency of the original wave? Okay, so I remember V equals wavelength times frequency, and I need the frequency to be twice as big. So the wave speed is going to be constant, right? That'll stay the same. Twice the frequency has to go up. So wavelength, in order to keep it consistent, would have to go down by 2 times, right? So half the wavelength. This one has a wavelength of L, so I need the wavelength to be 1/2 of the total length. So that would mean 2 full waves within the length. And the one that has 2 full waves within the length is C. There is 1 full wave, and there's a second full wave. So the wavelength has now shrunk in half, which causes the frequency to go up twice. And so that would end up with twice the frequency of the original wave. So it's just a manipulation of that wave speed equals wavelength times frequency. All right. So that's a nice piece on string instruments. Now let's talk wind instruments. So in wind instruments, I have a few different options. I can have, all of them have some kind of a tube. And then I'm creating a standing wave inside of that tube. However, I can create the standing wave inside of that tube either through having open ends or closed ends. So if I have an open end of the tube, that's open to the rest of the room air, right? So that's neutral air pressure. And we would say, since neutral is in the middle, that is a node. So here's an example of a neutral open. You can see right there, the wave has gone to neutral, right? It's back at even. Now, recognize sound waves are actually compression and rarefaction waves. So we're representing it as a transverse wave because it's easier to draw. But in reality, this would be compressions and rarefaction. So there'd be a compression right here. And then the rarefaction would be somewhere out here. And so this would be the neutral part. But neutral is at the end of an open tube because it's open to regular air pressure, and that is neutral. Okay, so an open end of the tube is always neutral. That gives me a node. That means if I have a closed end of the tube, that would give me alternating high pressure or low pressure, and that would be an anti-node. So that would be a spike. So here's one that's closed. It's either high pressure or it's low pressure. And so that's going to be an anti-node, one of the ends of the hump. And you can kind of feel that. If you imagine yourself playing a trumpet, you would put your mouth up against the trumpet. That closes the end. The side with your mouth on it is closed. And then when you play the trumpet, you do a little like kind of thing where you vibrate your lips together, make a little raspberry sound. And then if you put your finger up against it and you feel it, you can feel there's alternating high and low pressure, right? You're buzzing your lips, and that's creating a vibration. And you can feel the pressure on your lips, on your finger going high and then low, high, low, high, low, high, low. And that's why you're getting the vibration or the noise. So you have alternating high and low pressure, and that makes it an anti-node. Okay, so a closed end of a tube is an anti-node. An open end of a tube is a node. So if I have an open side and a closed side, I would have one node and one anti-node. So my 3 options are either a tube that is open, open. If it's open, open, then both sides have to be a node. And so then I would get these pretty normal looking one hump, two humps, three humps kind of things, just like a string. And so then the length would be half of a wavelength, or two halves of a wavelength, or three halves of a wavelength, or what have you. If it's closed, then it's the same thing, but it's starting from the antinode position. So this is still half of a wavelength. It just doesn't show one full loop, right? One full bump. So this would still be half of a wavelength, two halves of a wavelength, three halves of a wavelength. So for those ones, I can use the same old equation. The wavelength for the mode is equal to 2L over the mode. For open, open, or for closed, closed. Oh. For the frequencies, I can use the same equation. The frequency is equal to the mode times the wave speed over 2L. And the frequency is equal to the mode times the fundamental frequency. The one that's a little bit different is if it's an open end and a closed end. So I have one end that's open and one end that's closed. In that case, because I have a closed end, that has to be an antinode. The open end has to be a node. So now I'm going from high to neutral, right? Or going back the other way, neutral to high. And then if I continued that pattern, it would be high back to neutral, neutral back to low, and then low back to neutral. So that's 1, 2, 3, 4 sections total to make a full wave, not drawn to scale here. So the part that's the tube is 1/4 of the wavelength for an open closed tube. So the length is now 1/4 of a wavelength. Or the next option would be to do 1.5, so like 3/4 of a wavelength. So mode equals 3 would be 3/4 of a wavelength. Or mode equals 5 would be 5/4 of a wavelength. I get one full wavelength plus a quarter. In this case, it's half of a wavelength plus another quarter. So in this case, the modes are only going to be the odd numbers, 1, 3, 5, 7, because I have to go from a node to an antinode. And then my equations are going to change. Instead of having 2L on all those equations, now I'm switching it so that it's 4L on both of those equations. Otherwise, it's the same. I can only use the odd numbered modes. All of this is just based off this equation. Wave speed is equal to wavelength times frequency. If you remember this equation and you use this for everything, and then you just remember closed, closed, and open, open is going to be the half wavelength ones, and open, closed is going to be the quarter wavelength one. For the length, you'll be fine. You can just logic it out from there. And that's how I solve all of them. So I don't memorize those equations. I just remember the main core equations here, which are that guy. And then this one, that this is open, open, or closed, closed. And this is open, closed, or closed, open. All right. At the end, yeah. So let's do a little practice problem about playing a wind instrument. So wind instruments have an adjustable joint to change the tube length. Players know that they may need to adjust this joint to stay in tune, that is, to stay at the correct frequency. To see why, suppose a cold flute plays the note A at 440 hertz when the air temperature is 20 degrees Celsius. How long is the tube? At 20 degrees Celsius, the speed of sound in air is 343 meters per second. Okay, so I'm going to solve for the wavelength first, right? And then I'll figure out the length from that. So for part A, I know that the wave speed equals the wavelength times the frequency. That would be 343 meters per second equals the wavelength, that's what I'm trying to figure out, times 440 hertz. So the wavelength equals 343 divided by 440, 78 centimeters, 0.78 meters, 78 centimeters, but that's the wavelength. And remember, a flute is open, open. Both ends of a flute are open. So that means I need to find half of the wavelength for the length. So I'm going to do that divided by 2. And that gives me 39 centimeters. So it should be 39 centimeters cold. Now, as the player blows air through the flute, the air inside the instrument warms up because now it's coming from your body, so it's getting body temperature air, right, at like 98 degrees out of your mouth or something like that. Once the air temperature inside the flute has risen to 32 degrees Celsius, increasing the speed of sound to 350 meters per second, what is the frequency? So now I'm changing the frequency because I've changed the wave speed. So I have the same wavelength, right? That stays the same, but I'm changing the velocity. So for part B, I'm going to do V equals wavelength times frequency. My wavelength stays the same because I've kept the same tube length. So that's 0.78 meters. But now it's 350 meters per second equals the wavelength 0.78 meters times a new frequency, 350 divided by 0.78 is now 449 hertz. So I've changed it by 9 hertz, which could be pretty significant. That would sound a little bit pitchy. And then finally, for part C, at the higher temperature, how much must the length of the tube be changed to bring the frequency back to 440 hertz? So now I need to go back to 440 hertz. So I'm going to do the same thing as the first part, as part A. V equals wavelength times frequency. Now it's 350 meters per second equals, I got to adjust the wavelength, right? I got to adjust the length of the tube times the frequency is 440 hertz now. So 350 divided by 440. Now my wavelength is 0.795. Nope. Sorry. Wavelength is 79.5 centimeters. And then divide that by 2. 39.8. So now it has to be 39.8 centimeters as the length of the tube, as opposed to my original 39. The difference there, 39.8 minus 39, is how much must the length be changed? So I need to add 0.8 centimeters. So I have to extend the tube by 8 millimeters, which on a 39 centimeter tube is a significant percentage. So that's just kind of an interesting piece. I didn't really understand why players kept playing like before the actual concert. I thought it was just like practice, but it's like warming up, right? You're not just warming up yourself, you're warming up your instrument, which is kind of interesting. All right, for me, maybe not interesting for you. So let's do another stop and think. A tube that is open at both ends supports a standing wave with harmonics at 300 hertz and 400 hertz with no harmonics between. What is the fundamental frequency of this tube? Okay, so it has a harmonic at 300 and it has a harmonic at 400. Since I know that the fundamental frequency times whatever number gives you these harmonics, and there's no harmonics in between, the difference between them is 100 hertz. And so 300 hertz must be the third harmonic, 400 hertz must be the fourth harmonic, and then what am I multiplying by 3 and by 4 to get 300 and 400? That has to be 100 hertz. So the fundamental frequency has to be 100 hertz because it's open at both ends, so it should be straight multipliers. And 100 times 3 gives me 300, 100 times 4 gives me 400, 100 must be F1. All right, so let's talk about some interference in the real world. So we can have constructive and destructive interference. Constructive interference is when two wave sources are exactly one wavelength apart. So here I have a speaker and another speaker, and they're exactly one wavelength apart. So after this speaker goes through one full wave, it adds to the second speaker, and they are perfectly in line with each other. So they add together, and they go double high, double low, double high, double low, etc. Pure constructive. So that's going to be way louder, right? Those two speakers are going to give you greater amplitude, and you're really going to hear that, that music much louder. Destructive is when they are half of a wavelength apart, right? So I get a difference of 1/2 of a wavelength because then the amplitude or the crest of one gets countered out by the trough of the other. So in this case, I start with a crest and then I would go down into a trough. But because this next speaker starts half of a wavelength away, it starts with its crest, which is exactly opposite the trough. And then that continues for the next one. It goes trough, crest, trough. And this one goes crest, trough, crest. And so they keep canceling each other out and end up as no noise, right? Pure destructive interference because they're exactly half of a wavelength away from each other. So when the change of distance, when the distance between them is half a wavelength, it's destructive. When it's a full wavelength, it's constructive. And if it's somewhere in between, then it's like kind of constructive, kind of destructive, somewhere in the middle. All right. So let's do a little practice on that. Interference of sound from two speakers. Susan stands directly in front of two speakers that are in line with each other. The farther speaker is 6 meters from her. The closer speaker is 5 meters away. The speakers are connected to the same 680 hertz sound source, and Susan hears the sound loud and clear. So that sounds like it's purely constructive. The frequency of the source is slowly increased until at some point Susan can no longer hear it. What's the frequency when the cancellation occurs? Assume that the speed of sound in air is 340 meters per second. Okay, so right now, the speakers are 1 meter away from each other, right? So the change of distance is 1 meter. And at 680 hertz, well, let's start by figuring out the wavelength just to kind of compare and contrast. So I have V equals wavelength times frequency. 340 meters per second equals the wavelength times 680 hertz. Divide by 680, divide by 680. Wavelength equals 0.5 meters. So half a meter, and they are 1 meter away from each other. So that's 2 full wavelengths. Okay? And that makes sense. 2 full wavelengths is within an integer of the regular wavelength, so that would be purely constructive. The frequency is increased, so that 680 is going to have to go up, right? And I want the 680 to go up until she can't hear it. So that would be purely destructive. At this situation, it is 2 wavelengths. So I would need to shift it to 2.5 wavelengths, right? 2.5 wavelengths. Frequency, let's see, actually, I want to double check this. If the frequency increases, the wavelength is going to decrease. So actually, I need to go to 1.5 wavelengths, right? I'm turning up the frequency. So 1.5 wavelengths would be where it cancels. All right, I'm going to go down on my wavelength because the velocity is the same, wave speed's the same. So 1.5 wavelengths in 1 meter, right? 1 meter equals 1.5 wavelengths. Divide by 1.5. 1 over 1.5 is 2/3 of a meter. So now I need my new wavelength to be 2/3 of a meter. It was 0.5 meters. So now I'm going to do 340 meters per second equals 2/3 of a meter times the frequency, divide. 340 times 3 halves. (1.5) gives me 510 hertz. Uh-oh, I went the wrong direction. I thought that I was going the right way, and somehow I made a mistake. Oh, you know what happened? When I saw reduce the wavelength, 1.5 wavelengths in 1 meters, that's actually increasing the wavelength. So I made a mistake there. I went the wrong direction. Now I'm going to retry it with my original, which was 2.5 wavelengths in 1 meter. So now I change this, make it 2.5 wavelengths. 1 divided by 2.5 is 0.4. 0.4 meters. 340 divided by 0.4 is 850 hertz. So since I'm turning up the frequency, I have to get to 850 hertz, not 510 hertz. And so I tried it one way where I knew that I had to change it by half a wavelength. And I tried it at 1.5, and that told me 510. And then I did a BS check and said 510 is not an increase of frequency from 680. So then I did it half a wavelength the other way, which is 2.5 wavelengths, and then redid it, and that gave me a valid answer, right? Now I've turned up the frequency to 850 hertz. All right. So let's try a similar one. Now, 2 speakers are 3 meters apart, playing identical tones of frequency at 170 hertz. Sam stands directly in front of one speaker at a distance of 4 meters. Is this a loud spot or a quiet spot? Assume the speed of sound in air is 340 meters per second. Okay, so this one's a little bit 3-dimensional. That's 2-dimensional, actually. So let me just kind of sketch it out. I have 2 speakers that are 3 meters apart. Sam stands directly in front of one. So here's Sam at a distance of 4 meters. Okay, so he has one direction here that's 4 meters. And then the other speaker is coming this far out there. Well, I've got 3 and 4, and that's a right angle. And I happen to know that that's a 3, 4, 5 right triangle. So that's 5 meters. I could also use the Pythagorean theorem, but I recognize 3, 4, 5. So it's 5 meters from one speaker, 4 meters from the other speaker. That's still a change of distance of 1 meter. All right. Now I can do my wave speed equals wavelength times frequency. 340 meters per second equals the wavelength times the frequency, 170 hertz, divide, 340 divided by 170 gives me 2. So my wavelength equals 2 meters. And my distance is 1 meter. 1 is 1/2 of the wavelength. And half of the wavelength means it's going to be a purely destructive interference space. So that will be a quiet spot. Okay. So that is not a good place to stand for those two speakers because you'll get destructive interference because it's half a wavelength off from each other. All right. Let's do another little practice on a stop and think. These speakers emit identical sound waves with a wavelength of 1 meter. At the point indicated, is the interference constructive, destructive, or something in between? Okay, so they're 8.5 meters and 9.5 meters. That's a difference of 1 meter. The wavelength is also 1 meter, so they should perfectly align at that point. 1 meter with a wavelength of 1 meter is exactly 1 wavelength away, so that should be purely constructive interference. All right. Last idea that we are going to talk about is beats. So a beat is where you're playing two frequencies and you can hear them kind of coming together. So it'd be like you're playing something and it's actually more be like a and I'm doing about 2 beats per second there, 2 per second. So that would be a beat frequency of 2 hertz. To find the beat frequency, you can take the 2 frequencies that you're playing, subtract them from each other, take the absolute value of that. That's how many beats per second you'll hear. So frequency 1 minus frequency 2, and that gives you your beat frequency. So here's kind of how that works. I have 2 sound waves of slightly different frequencies. The beats that I'm going to hear are where there is good constructive interference. So that would be right there, and right there, when you superimpose them together. Here would be kind of like the quiet part. So when I'm like, when I'm not doing the, it's a really nice look for me. That would be when it's destructive there. So this one has 2 beats in whatever period of time this is. All right. So you hear 3 beats per second when 2 sound tones are generated. The frequency of one tone is known to be 610 hertz. The frequency of the other is, okay, so 3 beats means that the other tone has to be 3 hertz away. 3 hertz away from 610 could be 607 hertz, or it could also be 613 hertz. Either one works because both are 3 hertz away. So both of those options would give you a beat frequency of 3 beats per second, 607 or 613. That is B and C, and B and C is F, either. All right. And that, my friends, summarizes superposition and standing waves. And now you are ready to do a few practice problems and be done with waves and Unit 10. We did it! Boom! Great job, team. There we go. Have fun, enjoy. And I'll look forward to seeing you shortly. Bye, friends.